Okay, our glomerular filtration rate, or GFR, this is something that's really important in the medical world. You'll often be testing somebody's GFR to find out if their kidneys are working correctly. But what we want to look at is how does the body maintain this normal amount, 125 milliliters per minute, with a normal systemic pressure of 120 millimeters of mercury. Now remember, we have a hydrostatic pressure of blood that is going to be going into the renal corpuscle here, and then we have this hydrostatic pressure pushing the filtrate, or the blood, out into the filtrate, then the filtrate going and being reabsorbed and then eventually being turned into urine. And so the rate that we want this to happen is at 125 milliliters per minute. But that would only occur as long as our pressure here is 60 millimeters of mercury, and our overall systemic pressure would be 120 millimeters. So that's what we're pushing it into our kidneys at. So what happens if our blood pressure drops or rises? Well, if it rises, then obviously what's going to happen, we're going to push out more filtrate, and this number is going to go up. And if we don't do something about that, we could become severely dehydrated. Or if this number drops, then we could not filter our blood properly. So either one of those situations, we've got to somehow adjust. So autoregulation means what is it our body's doing naturally without us necessarily having to consciously do something about it. So one of the autoregulatory methods we're going to talk about is what goes on in the muscles themselves of the afferent arteriole. All right, but again, let's make sure we understand this is the amount of filtrate we're producing in a normal rate, 125 per milliliter per minute. If our blood pressure rises or drops, it throws this number off. So how does our body adjust to get back at this number? And one of the main things it does is it adjusts the size of the afferent arteriole. Okay, notice if our pressure rises above 120, then we know that we're going to actually get too much GFR there. So what we need to do to slow that down is we need to constrict this, because if we constrict it, we constrict the blood flow in there, therefore we constrict the amount of glomerular filtrate that we actually release. Okay. Well, if our pressure drops below 120, then our glomerular filtrate rate will also drop, and again we want it at about 120, so if it drops down to 104, then we're not going to be filtrating properly. So what we're going to have to do is actually get more blood here so we can get more filtrate out of it and raise our GFR. So then how we're going to do that? Well, somehow we're going to have to cause our afferent arteriole to actually increase in order to do that. Okay, and by increase I mean we need it to dilate. So here we see it dilated, and here we see our increase of our GFR. Well, one of our autoregulatory methods that we use is the myogenic mechanism, which is basically using the constrictive and dilating features of the smooth muscle themselves. And so we know that if we get pressure in here, we start stretching the walls. And if we stretch the walls, we get a natural vasoconstriction. If we relax the blood going in here, we get a natural dilation. So we have this autoregulatory
vascular smooth muscle cells.
So we have this autoregulatory mechanism. If I have a lot of pressure in here, this is going to automatically constrict, because a lot of pressure in here is creating a pressure against the walls, which causes it to constrict. If it constricts, then it becomes smaller, therefore it limits what we're pushing out, therefore my GFR will drop. Now, let's say that my blood pressure drops. Well, if my blood pressure drops, I don't have as much pressure against the wall, therefore this dilates. If it dilates, then I get more blood here. Now, if the pressure dropped and I didn't do anything, I'm not going to get as much filtrate, therefore my GFR is going to drop. But if my pressure drops and I don't get as much pressure on the wall and this dilates, then I'm automatically going to get more blood in here. More blood in here is going to allow me to might make more filtrate, which will bring me back to the normal amount of 125 milliliters per minute. Okay, so the next mechanism for regulating our GFR is called the tubuloglomerular mechanism, and it involves a really important structure called the juxtaglomerular apparatus. Now, if we break the name down, juxta means next to. So what are we next to? Well, we're next to the glomerulus, so we are the juxtaglomerular apparatus. And what that does, that involves cells in this junction right here between the afferent and the efferent arteriole, and cells from both the ascending loop of Henle, which is turning into the distal convoluted tubule at this point, and cells that are actually affiliated with the afferent arteriole. If we have a high glomerular filtration rate, higher than 120 milliliters per minute, then one way we can monitor that and adjust it is the cells that are called macula densa cells. These cells here are monitoring the osmolarity of the filtrate. And of course, the osmolarity means, what's the concentration of the ions in that. So something with a high salt solution would also have a high osmolarity. Something that was very dilute would have a low osmolarity. So these cells are basically monitoring the ion content of the filtrate at this point. Okay, so one thing these cells do is if they monitor that there's a high GFR or high osmolarity for high GFR, then what they're going to do is actually release a vasoconstrictor. And what it's going to do is going to decrease the diameter of that afferent arteriole, which is usually, bigger than the efferent arteriole. But remember, even the myogenic mechanism, the stretchability of it was also monitoring it. So again, we're going to, if we have a high flow, then we're going to release chemicals that cause this to constrict. If we constrict this, then of course we make a lower flow. Okay, so what does the vasoconstrictor do again? Well, ultimately it decreases the filtration rate. And so part of how it does that, it slows the filtrate rate, the tubular filtrate rate, and the reabsorption. So remember, we filtrate, then we reabsorb. So the reabsorption of the ions increases. So again, we've constricted this, so we slowed that rate, the filtrate rate, and then we're giving us more time to reabsorb the ions, which is going to lower the osmolarity for the next time we monitor that. Okay, so once we've constricted, we've lowered the flow, increased the reabsorption of that. That's going to drop our osmolarity. We're going to then detect that we have a lowered osmolarity, and we'll quit releasing so much vasoconstrictor. Now again, remember, this vasoconstrictor is constricting the afferent arteriole, which is always, in normal situations, a bigger diameter than the efferent arteriole. Okay, what if when we're monitoring this, we have a low flow rate, so we're going to be less than 125 milliliters, and so therefore we're going to have a lower osmolarity, which is what the macula densa cells are releasing. So first thing, if it measures a low, and it's very low, it's not just correcting, but it's a consistently low osmolarity, which means a consistently low GFR, then it's going to definitely quit releasing any vasoconstrictor, so this can get larger. But then the next thing it's going to do is the macula densa cells are going to release something that triggers these cells, which are called the granular cells, to release a chemical called renin. Okay, so renin is released into the bloodstream. It converts a blood enzyme called angiotensin 1. It converts it to angiotensin 2. Now there's a series of steps that triggers that, so we will be talking about that in a future video, so I'll come back to that. But when we do convert angiotensin 1 to angiotensin 2, then what angiotensin 2 does it actually causes the efferent arteriole to further constrict. Now remember, it's already smaller, but if I constrict it even further, then what that does is that creates a higher pressure of the blood going into the glomerulus, because this blood vessel is already bigger than that. So if I cause that to constrict even more, then it increases the hydrostatic pressure, which means we're going to push out more filtrate, because remember, we're trying to overcome a low filtrate. Now, what this is also going to do is it's going to, making this smaller, is going to lower the blood flow out of the glomerulus, because I'm constricting that area. But again, why are we doing that? Because we're really trying to increase the hydrostatic pressure of pushing the filtrate out so we can increase our glomerular filtration rate. So anything I can do to push more out here will increase the rate, because I don't want to keep it low forever. I want to bring it back up to that 125 milliliters per minute. Okay. Another real important mechanism to regulate our glomerular filtration rate is our control of our sympathetic nervous system. So we know that
During normal daily activity,
we know that all of our blood vessels have neural sympathetic neurons running to them that will cause them to constrict. Now this is particularly important if we have a major blood loss, because if we have a major blood loss, we really can't afford to lose more fluid from the body. So major blood loss, usually due to an injury or something, would cause our sympathetic nervous system to kick in, or fight or flight. And then what that's going to do, that's going to constrict both the afferent and the efferent, which means we're going to basically shut down blood from being filtered here until we can correct the situation and, maybe increase our blood volume again in the case of a blood loss. Now, if serious illness or even being an emergency will also cause us to stop this process till the emergency's over, because again, the sympathetic, being part of our fight or flight autonomic system, is going to constrict both the afferent and efferent arterioles or within this glomerulus. And of course, what I should say is this afferent arteriole sending blood to the glomerulus, the specialized capillary, and receiving blood from the glomerulus. So if I can shut down this system, I'm not going to filter fluid out of the blood, even though we know when we do that, we reclaim most of it. But if I have a major blood loss, I can't afford to do that. And also, if I'm in an emergency, I need to shunt my blood towards the things that's going to get me through the emergency more than send the blood here where I'm filtering it. When I'm in that rest and digest stage, then that's the best time to do this. So let's talk about that pathway that we kind of alluded to earlier, where we had the granular cells. Remember the cells that were around the afferent arteriole, part of the juxtaglomerular apparatus. We said that they released renin and eventually led to angiotensin II being released. Well, the other thing that we want from this pathway is this hormone called aldosterone, and we'll see why in a few minutes. So let's look at this pathway here from renin to aldosterone, and it's a little bit you should be a little bit familiar if you understood a little bit about the blood clotting cascade that we talked about, where we went from fibrinogen to fibrin. So just like fibrinogen was a plasma protein that needed to be converted to fibrin for the clotting process, well, we have a plasma protein called angiotensinogen that needs to be converted in the blood to another chemical called angiotensin I. So renin is what converts angiotensinogen to angiotensin I. Okay, the next thing is it happens mostly in the lungs. As the blood circulates through the lungs, angiotensin I then is converted to angiotensin II by ACE, angiotensin converting enzyme. So this enzyme converts angiotensin I to angiotensin II. Then angiotensin II does the things that we had mentioned before, constricting further constricting the efferent arteriole, which is going to end up increasing the glomerular filtration rate. Okay, another very important job of the hormone aldosterone